All right, are you guys excited? We are finishing this month-long unit today. I'm pumped. Okay? And what we're going to be talking about today is going to seem very, very different because for the most part, we're not going to be talking about acids and bases in this last section here. We're going to be talking about the solubility of solids. Now, what does that word even mean? The ability to do what? Dissolve. Yeah. Okay. So instead of acids and bases in this part, we're going to be talking a lot about solids dissolving. How well do they dissolve? Okay. As an example, okay, here's a solid, here's it dissolving. Let's just make sure that we remember that when ionic compounds, which is what we'll be dealing with, dissolve, you could also say that that process is the solid ionizing, okay, breaking down into its ions. I want you all to notice that this equation had to be balanced. We have not had to worry about balancing equations for like a month, okay? Because all of our acid-base reactions, just the nature of how they do, they're always in 1-to-1 to 1-to-1 ratios. So we haven't even had to think about balancing in a while. Today we do. Now, would you guys tell me, please, if I asked you to write the equilibrium expression, products over reactants, for this reaction, okay, I'm not asking you to solve for anything, what would that expression look like? What would be in the numerator? Okay, yeah, bismuth, that's an element we don't deal with very often. Squared, good. Times, okay, sulfide, very good. Products over, be careful. Okay, solids are excluded, right? So what's there? Yeah. All right. Well, guys, an equilibrium expression for a solid salt ionizing has a special, its own special variable. It's called KSP. SP for solubility product. Okay, now think about it, guys. We have had a lot of Ks. Ka, Kb, Kw. At the beginning of the year, we had Kc, Kp. This is our last final type of equilibrium constant, but it's still just products over reactants. And since a KSP is always written for some reaction of a solid breaking down into its ions, the new denominator will always be 1. KSP expressions, if you just think of it like this, KSP expressions can always be written in just one line like this. Always. Okay? So we're going to be writing those expressions a lot today. Okay? And we don't include solids, of course. We also exclude liquids, but we're not going to be seeing liquids in this part. So what kind of problems could you see with a KSP? Guys, you will be asked to solve for one of two things in any KSP problem. You'll either be asked to solve for the value of KSP, that's very common, or you might be asked to solve for the solid's solubility. And we're going to use a variable of a lowercase s for solubility. Okay? And I want to just call your attention. I want to make a connection between this section and acid-base. Okay? Solving for S in a KSP problem is the same thing as solving for X in a WOMIX problem. Okay? I could have just as easily used the variable X. I only chose the variable S to kind of distinguish KSP problems from acid-base problems, but it's solving for the same thing. So what do I mean by that? Okay, let's look at a sample problem here. All right, I'm going to do number 1 with you, and you're going to see some connections, some of the same skills that you've become very good at from this acid-base section that you can use here. Okay, so bismuth iodide. We're going to do this problem together. All right. If I were listing out my major species, guys, I want to just make sure you get this. There they are. I want to explain to you why I did not break that apart. Okay, because earlier in this chapter, anywhere that we've had a salt, we have split it apart when we've listed our major species. Well, the reason I'm not splitting that one is because this is not a salt in solution. It's a solid, like just a solid sitting on the counter. The ones that we've been splitting apart all along have been in solutions. They weren't in solid form, they were in aqueous form. I'm going to keep that together because it's a solid. These are my only major species. Here's my reaction for how does this solid break down. Very simple. Now bismuth, that's an element we don't work with a lot. Okay, and if you're looking at the periodic table to try and figure out, well, what is its charge when it's an ion, looking at the periodic table is not going to help you. So you don't know this one, but you guys know iodide, right? What is this charge? What's the charge of bismuth have to be here? +3. Okay, very good. Iodide, of course, is -1. Is it balanced? No, and it needs to be. Okay. Oh, your favorite 3 letters. Okay. But actually, these are much simpler, quicker ice tables. Do solids get included in equilibrium expressions? Nope. Is this ion in my list of major species? Nope. How about this one? Nope. Okay. Think of this like a WOMIX table, a WOMIX ice table, or even let's change that last letter, a WOMIS, because now I'm going to use S instead of X. So what do you think I should put under here? Plus S. Be careful. What do you think here? Good. Something we have not had to worry about because our coefficients have always been 1. Okay. Tell me, please, what would the K expression, KSP, for this reaction look like? Okay. To what power? The first power, okay. Times iodide to the third power, okay. Let me substitute these things in there. set everything up. Let's come back. Let me go back to the original problem and see what was I actually given here. The solubility. Guys, this value is S. That is S. Now, don't write anything down yet. Just look up for a second. Do those units look familiar to you? Moles per liter, that's the same units as what? Molarity. Solubility and molarity are essentially the same thing. Think about it. Solubility is how many moles of this solute will dissolve per 1 liter. So I have S. All I have to do is plug it in anywhere that I see it. So I multiply it and raise it to the power. I'll save you the time. Here's what the value comes out to be. K, good question. K does not have units. Okay, so you don't have to worry about it. All right. Now, before you go on, I want to just make sure you understand this number and what it represents. Would you guys say that this is a big number or a small number? Small. Think about what that means. Any kind of K, whatever the number is products over reactants. If a K value is very small, what does that mean for this equation? Am I getting a ton of product or very little, hardly any? Hardly any. Well, guys, what does that even mean? Look at this particular reaction. If this reaction is barely ionizing, what's a word we learned in first quarter? You learned in Chem 1 as well. What's a word you use to describe a compound that hardly dissolves at all? Insoluble. Okay. Do you guys remember from first quarter? You didn't have to memorize them. We had those solubility rules that said, this compound is soluble, this one isn't. Well, guess what? This is where those rules come from. This being such a small number, this would be considered an insoluble salt. Now, please don't ask me, what is the magic KSP number where something goes from being insoluble to slightly soluble to very soluble? I don't know. Okay, but I just wanted you to understand the meaning of this number. Okay. I'm going to have you do the rest of these on your own. Let me just give you one quick little bit of guidance. Put your eyes on this line right here. In this particular problem, I was given the value of the solubility. You will have other problems where you are given the KSP and you're supposed to solve for S. You could do that, right? All of these problems, set them up the same and then see what is it that you're given, where can I plug it in? Okay. 2, 3, 4, go. So here's your answer for number 2, and look at that number, guys. How would you describe, based upon this number, how would you describe this compound? Super insoluble. Well, if you go back and look at our solubility rules from first quarter, it says most phosphate salts are insoluble. Yeah, you bet they are. Okay. Keep going. Okay, there's number 3. Check it. Guys, this is what I was saying to solve for S, think, because remember I said solving for S is the same thing as like solving for X when we do a Womix problem. If you wanted to, you could graph this, absolutely, but since this is more simple than we're used to, and you have a cube root function in your calculator, you didn't have to graph it. Also, if you're being asked to solve for solubility, do you have to express your units like this? Could you write a capital M? Sure. Okay. Typically, though, you'll see solubilities expressed with units of moles/liters, but if you would rather put a capital M, fine. Okay. So that's number 3. There's number 4. Check it. All right. Now, ladies and gentlemen, would I expect you to do this in multiple choice? No. Unless the numbers were significantly simpler, probably not. This would be most likely free response. Now, what could I ask you in multiple choice? Maybe I ask you something like this. Maybe I ask you to compare, that's what I mean by relative, compare the solubilities of 2 different compounds, okay? Like, I give you 2 compounds and I say, which of these salts, either I say is more soluble or has a greater solubility? Well, it depends on the situation. Sometimes it is as simple as comparing the KSP values. The bigger the KSP, the more soluble the compound is. However, there's a little bit of a snag with that. You can't just compare the KSPs of any 2 salts you want. You can only do that if the 2 salts that you're comparing, the way I say it is, if they fall apart into the same number of ions. What do I mean by that? Well, for example, when this salt breaks down, how many ions are on the product side? How many pieces? 3. 1 lead ion and 2 bromides. Okay, that falls apart into 3 pieces. How about this compound? Silver carbonate. How many ions? 3. Remember, 2 silvers and what? Remember that polyatomics stay together as one chunk. So 2 silvers, 1 carbonate, that's 3 ions. These 2 compounds, ladies and gentlemen, I could compare their KSP values. But what if I had this? How many ions does that salt break down into? 5. Okay. If I was comparing these 2, I cannot simply compare their KSP values. So what do? I have this very cryptic phrase here. You have to do the math. What does that mean? Do the math. Okay. Do the math means solve for the solubility. Solve for S and compare those numbers. Okay. If you go and look at the problems we just did, numbers 3 and 4, you solved for S. Okay. So if they break down into the same number of pieces, you can compare KSP. The one with the larger KSP is the more soluble salt. If they fall apart into different number of pieces, then you have to solve for S, solubility, and compare those. The one with the larger value for S is the more soluble salt. Okay. All right. is a term we have seen before. Let me tell you where we saw that term in the past. That term came up when I introduced to you what a buffer system is. So let's review that. That's good review for our test next week. There's two types of buffers in this world, guys. What is one type of buffer? What are the two components that have to be there? A weak acid and its conjugate base. Okay. So, for example, my favorite weak acid. And what is HF's conjugate base? F minus. And in a buffer system, usually that conjugate will be within a salt of some kind. This would be a buffer system right here. Do you all see that they have an ion in common? Yeah, they both contain fluoride. Okay, now we're not talking about buffers here. I just wanted to refresh your memory on when we saw that term before. Okay. Here is the situation. The problems on the previous, or 2 slides back, those short problems we were doing, those salts were being dissolved in pure water. What if they're not? And I'm going to illustrate how to handle that situation with a practice problem here. We'll do this one together. Number 1 says, calculate the solubility. So first and foremost, I know I'm trying to solve for S at the end of this problem. Calculate the solubility of solid strontium sulfate, and I give you the KSP. Now guys, imagine if the problem ended right there, and there was nothing else written after it. Wouldn't this be exactly the same situation as we saw in numbers 3 and 4? If the problem ended right there? Yeah. But it doesn't. Okay? We're not dissolving this solid in pure water. We're dissolving it in a beaker that already has something in it. And it's not water. It's a solution of 0.01 molar sodium sulfate. Do you see an ion in common? I do. Sulfate. Okay. Let's think about our major species here. How do you handle writing out this guy? Keep him together or split him up? Keep him together. Why? He's a solid. Okay, we of course always have water. What about this compound? Why separate it? Because it's in a solution, okay? This is a salt as well, but it's a salt that's in solution. So you can split that one up. Okay, now, KSP problems, guys, figuring out what the reaction is not nearly as complex as it is in acid-base. In a KSP problem, your reaction will always be the same. The solid yields ion-ion. Which compound do you think is the one that I really care about here? This one, the solid. Okay, so here's how it breaks down. Strontium ion, sulfate. Is it balanced? Yep, okay, great. Do our little ice table here. We don't care about solids, we never do. Is this ion right here in my list of major species? Yes or no? Nope. How about this one? Yes. I'm not going to put a 0 there. There is some. Now, if you're wondering, is this, do I put moles? Do I put molarity? What do I do? Remember, this is very much like a WOMIX problem, except let's change that last letter. This is like a WOMIS. A WOMIS problem. What kind of numbers do you put in this table? Molarities. Okay, well there it is. 0.01. What should I put under this right here? Plus S. Plus S. How nice, we've got all coefficients of 1. Okay. Let's write out our KSP expression. Pretty simple. And I'm just going to sub in these S's. Okay. We were given the KSP value, which I can plug in right there. Probably want to graph this one. So if you put in the KSP value in Y1 and you put this whole thing into Y2, to save you the time, here's what S comes out to be. That's it. The only thing that made that slightly different from what we had done previously was just this wasn't a 0. That's all. No big deal. Okay. Now, it is not enough for me personally that you just can do this math. I want you to understand what's going on here from a conceptual level, okay? Because what if I were to ask you this? Does this solid have a better solubility in pure water or in a beaker containing a solution of sodium sulfate? Well, you could, if you wanted to, calculate the solubility with this as a 0. That would be in pure water, and get a value for S. And then compare it to what we just found. You could do that, or you could explain it from a concept perspective. Guys, think about this equation right here in terms of Le Chatelier's principle. Look at this equation. If I am going to put this solid where there is already some of this sulfate, imagine it's like adding more of that product. Which way will this shift? This way, to the left. Think about what that means. If this reaction is shifting more toward the solid side, is this dissolving better or worse? Worse. Okay? Guys, any compound, it doesn't matter what the compound is, any salt will have a decreased solubility if one of its ions is already present. It will not dissolve as well. This would have a better solubility in pure water than in this environment. I want you to understand that conceptually. There is a second problem where the coefficients are not so nice. You do this one on your own. Check your answer. If you are graphing this, this shouldn't make a difference, but it just makes your calculator happy. Put an extra set of parentheses around this term and then around this term as well. Should that change anything? No, but last class some people didn't have those parentheses but had everything else correct and they were still getting the wrong answer. I don't know. So, ladies and gentlemen, we just did the math associated with the solubility of a salt when there is a common ion present, which could be put in context of, is this salt more soluble in pure water or in this solution? Here is something else I could ask you. I could ask you if a salt's solubility is affected by the pH of its environment. Maybe even more specific, maybe I ask, will this salt dissolve better in water or in an acidic environment? Okay? Don't read that. Don't even read it. Don't even look at it. It will make much more sense if you read it later. Just don't even look at it. Focus here. All right? We've got an ionic compound. This is calcium. Do you guys remember? This is not one of the polyatomics I had you memorize, but it is on your polyatomic ion sheet. Do you know the name of this guy? It starts with an O. Oxalate. It is called calcium oxalate. Okay? When it ionizes, this is what happens. Well, guys, let's imagine that I am dissolving this salt not in a beaker of water, but in a beaker of hydrochloric acid. Okay? Hydrochloric acid, strong or weak? Definitely strong. Will that beaker have lots and lots of H plus or very little? Lots and lots. Okay. If that is the case, and there's lots and lots and lots of H plus floating around, here's what's going to happen. Every time one of these oxalate ions is released from the solid, it is going to pair up with one of these H plus ions that's floating around, and it's going to form this. This, ladies and gentlemen, is an acid right here. Is that one of our strong acids? No. So it must be, okay, what does it mean to be a weak acid? Does not dissociate much. So let's put that in some other words. Does this compound like to be together, or would it prefer to be apart? Which one? It likes to be together. Weak acids, you just said, don't dissociate much. That means they would prefer to be together. What I'm saying is this reaction in yellow is very readily going to happen in that direction. Okay? Because these two are going to attract to each other like magnets. Now, so what? Who cares? Well, what I'm asking you is, what is going to happen to this salt's ability to break down if this is present? Every time one of these oxalate ions is released from the solid, it's stolen away, captured by this H plus to create this. Come back to the equation in purple. Think Le Chatelier. Every time this ion is being created, it's being stolen away by H plus ions. If this reaction, when it runs one time in the forward direction, this guy's being taken away, I'm constantly removing product, will this shift? Yes or no? Which way? To the right. You are correct. Now what does that mean? The solid is going to break down more and more and more. Does this solid dissolve better or worse in an acidic environment? Better. This big arrow I've drawn here is the process of that salt dissolving. So this would be a salt. You could say it one of two ways. You could either say it has improved solubility in an acidic environment, or you could say its solubility is affected by the pH of its environment. I'm saying the same thing. Okay. Let me give you some other examples. How about this salt, magnesium fluoride? Imagine this salt in this position right here. And think about the possibilities of these two reactions. Which part of the salt should you be focusing on? Okay. Forget about the two, ignore it. This is just a fluoride ion. H plus and a fluoride ion, do they go together well? Why? It forms a weak acid. So guess what? This salt is affected by the pH of its environment. Here's another one. Iron 3 bromide. Tell me what you think. The big question is, will the second reaction in yellow happen or not? Why not? Yeah, a bromide ion in this position right here and a hydrogen ion are not going to link up. Why not? Tell me again. It's going to form a strong acid. Guys, this would be a salt that dissolves just as well as in water as it does in acid. pH does not affect its solubility. You will see these kinds of questions in multiple choice. It'll say, which of the following salts has its solubility affected by pH? You are looking for a salt whose anion could form a weak acid. That's what you're looking for. Okay? Okay? All right. Last topic. Get excited. It's on precipitation. There's some concept and some short math, and then we're done like dinner. Okay? Precipitates, ladies and gentlemen. What state of matter is a precipitate? It's a solid. Okay? And it might look something like this, although this may not look like a solid to you. It is. Okay? Just to make sure, because this is kind of a pet peeve of mine, precipitation reactions, it is not pouring two liquids together and getting a solid product. What is it? Pouring two solutions or two things that are aqueous together and you get a solid product. It just bugs me when people say you pour two liquids, because that's not right. Okay? You are going to be given situations where it'll say, this solution is combined with that solution. Will you get a precipitate, yes or no? Prove it with math. Okay? You are going to do that by solving for capital Q, which in this chapter they call the ion product. Guys, we have actually seen this before. We called it something different though. We called it, the first time we saw it, the reaction quotient. That's why it has a Q as its variable. Bells may still not be going off in your brain, and that's okay. Let's see if this rings a bell. Q is calculated exactly in the same way that K, your equilibrium constant, is calculated. Products divided by reactants. Are some of those bells starting to jingle a little? Do you all remember what makes Q and K different if they're calculated the same way? K is what kind of molarities? At equilibrium, Q is not at equilibrium, and you're right, usually it's going to be initial conditions. Once you get a number for Q, guys, it's easy. If Q is greater than KSP, yes, we'll get a precipitate. If Q is less, no, you won't. If they're equal, all you have to say is, we are at equilibrium. And I have a silly little memory trick to help you remember this. Okay? Let's look at a problem. We'll do one together, and you'll do the other one on your own. This looks really long. It's not. These do not require ice tables. Okay? Let's do this one together. It says, a solution of this volume, this molarity. Do you know what element that is? It's not cesium. It's cerium. Not cereal. Cerium. Cerium nitrate. That's an element we don't deal with a lot. It's down in the lanthanide elements, down at the bottom. Okay, this solution is added to this volume, this molarity. Here's another one you've maybe never seen before. Potassium, this is a polyatomic ion called iodate. Potassium iodate. And here's the question. Shush. Will cerium iodate precipitate? Yes or no? Okay. Well, ladies and gentlemen, KSP problems, no matter what kind it is, they always start the same way. You write a reaction for the solid breaking apart. Which compound do you think is the one that I actually care about here? Cerium. Why did you pick this one? You're right. Yeah, it's asking about it. It's also the one that we have the KSP for. Whatever compound you have the KSP for, that's the one you care about. Fine. So, here we go. Let's write a reaction for how it breaks apart. Now, neither one of these are we particularly familiar with. Cerium. There was another compound that had this formula. Can you tell me what cerium's charge is? It's +3. Nitrate is -1, and we know that one. Right? Okay. Iodate, polyatomic ion, you may never have seen before, but what's its charge? -1? Because we know potassium is +1. Is that balanced? No. Okay. Let's write a Q expression, which, guys, is exactly the same as a KSP expression. What should I write here? Okay. Okay, to the first power times iodate. Okay. All I have to do is find Q, and I can answer this question. We need molarities. Well, where is cerium coming from? Which compound? Okay. And you might say, oh, awesome. Here's a molarity for cerium. I'm just going to plug it in. It would be nice if it were that easy. Okay. But here's the deal. Let me use one of my bazillion coffee mugs for this. All right. Ready? Here's cerium nitrate. Here is potassium iodate. The molarities that are written in that problem are the molarities of each solution when they are separate. This Q that I'm supposed to be finding, these initial molarities, are not when they're by themselves. It's at the initial moment they are poured together into one big container. So, let's go back to basics here, ladies and gentlemen. What do brackets mean? Which is what over what? Moles over liters. Okay. Somebody tell me, given this information, how many moles of cerium are there? You can do this. You've calculated moles and millimoles all the time. You can do this. 3 millimoles. Okay, sounds good. Over what volume? Let me come back to the little demo. Over what volume? Total. How many milliliters is that? 1,050? Okay. Let's do the same thing with iodine. Tell me. Now your eyes should be here. How many millimoles? 12? Okay. Over what volume? Same. Don't forget to cube that number. Guys, type all that in. Tell me what you get. What'd you get, Claire? Okay. Sounds good? Is this number greater than or less than the KSP? It's greater than. Look back in your notes. What does that mean? Then yes, we will get a precipitate. Yes. Okay. Are you ready for the super silly memory trick? To remember, if Q is greater than KSP, yes. Okay. Here is the super silly way to do this. Think of the letter Q as a duck. Q for quack. That's why duck. Okay. If Q is less than KSP, think of that as like its beak is open. Okay? This is a rabid duck who is going to eat anything in its pathway. This duck is going to eat the KSP. Okay? If that happens and it eats the KSP, there will be nothing left. No precipitate. If the duck has its beak closed, it is not going to eat the KSP, and there will be something. In other words, there will be a precipitate. Okay, it's not perfect, all right? It's not great. One of my former students came up with it. I think it's kind of cute, right? Now, if you want the, why is this, really, why is that the case? Let me explain it to you this way. Ready? Q is greater than KSP. Guys, I want you to think of a Q that is bigger as being too large, too much. We have made, if Q is too big, that means we have made too much product. We've gone too far this way. How do we fix that problem? Which way should we go to fix it? We need to go back. Well, guys, what does going back mean? Think about, look at this reaction. Going to the left, you are creating more solid. If if Q is less than KSP, that means we have not made enough product, so we need to make some more. The solid will break apart. No precipitate. Okay. You guys do the second one. It's the exact same thing, and then we can call it a day.
Call it a chapter.
Tra-la-la. We're done. And ladies and gentlemen, our month of work is finished. Woohoo!